So if I were going to ask you probably if you want to dissolve the most sugar possible, dissolve sugar in water, you probably think if you heat it up, more sugar will go into solution. And you're right. So in that case, the solubility of sugar is higher at higher temperatures, and the solubility of sugar is lower at lower temperatures. So I don't know. You just probably have that intuitively in the back of your mind. So that's one of the things we're going to talk about. The effect of temperature in trying to dissolve a solid like sugar in water. So when we talk about solubility, what do we mean? That means actually the amount of solid that you can dissolve in solution. And it doesn't have to be solid, but we're going to start with solid. So, for instance, I kind of tease, if this is my water, my beaker full of water, and I'm going to add sugar, okay, if I have a sludge down here at the bottom, there's my sludge of sugar, so that's sugar, I'll put an S for solid, and I've stirred it and everything. Basically, I have reached the limit of how much solid. I'll put sugar AQ here. Now, only so much sugar can be held by the water at that temperature, right? So that's the solubility of sugar. So I've got videos today. Oh my gosh, I'm gonna try. I'd like to get through this whole part, but we'll see. I definitely. If you see sludge at the bottom, like this sugar sludge, or in the case of the video, they kept adding sodium chloride until they had something at the bottom. We're actually going to call that a precipitate. That sludge is a precipitate at the bottom. Then that means that your solution is saturated. It just means at that temperature, it can't hold anymore. Now, before I go too far, I want to tell you that the process is dynamic. And that means to say that the little particles down here of sugar in their solid state and the little particles of sugar suspended in their aqueous state, they don't stay that way. So, for instance, I could do a down arrow to show you that some of those aqueous sugar particles are going to precipitate. And I could put an up arrow to show you that some of those solid sugar particles are going to dissolve. It's dynamic, which is kind of fun, right? As long as I draw those arrows with the same length, okay? Or I know the other day we talked about, equilibrium vapor pressure, where the amount of evaporation is equal to the amount of condensation. It's a similar thing, very similar. So saturated solutions. We have an unsaturated solution. That would be where there is no precipitate at the bottom, and I keep adding more sugar and it dissolves. That must have been before I added it, it was unsaturated. It's not at the maximum amount yet. And then here's one of my favorites, super saturated. We have a few super things in physical science, and this is one of them. Super saturated, and actually this is an example of a super saturated solution. These are, I've got enough for everybody to play with. I don't know if I trust you guys back there. So don't do anything with it yet. Be gentle. I know you will. I know you will. It's a super saturated solution. So one of the things about super anything is that it's kind of unstable. So this is kind of unstable. Super saturated solutions. And you'd be like, well, how did they get more? I think this is sodium acetate. How did they get more sodium acetate in there than would dissolve? And it's not like magic or anything. It's just pretty much under the kind of the warming and the cooling process. So I've got some videos to kind of show you super saturated. Again, super saturated conditions are generally unstable. So let's take a look at these. Kind of like we did with regard to evaporation the other day. At first you have just total evaporation. This is when the solute first meets the liquid. And then you can tell that the red is still a little bit longer than the black. The black actually is precipitation. So the middle one, you still have a little more going into solution than coming out of solution. And then finally, we kind of have this equilibrium where the amount that's dissolving is equal to the amount that's precipitating. Okay, and you would have a saturated solution. So this actually, I think, is what you guys have. What you guys made warm. Generally, and it's the case with sodium acetate. We generally think if I heat it back up again, more is going to go into solution than it otherwise would. But that's not always the case. This is what I put up over here. Literally, if we kind of think of the process that we go through when we dissolve something, is we take the solid solute, doesn't have to be a solid, but in this case a solid solute, liquid solvent, and then on the product side we end up with a solution. So this would be on our way to saturation. Here when we have like a double arrow with the same length, okay, so this means the rate of dissolving is equal to the rate of precipitating. This is precipitating over here on the left. This is dissolving over here on the right. When those rates are equal, our solution is saturated. And we have the maximum amount of grams of solute per 100 mils of water that will probably So if we think of adding heat, or if something's got to be heated up, we can think of putting heat as on the reactant side. If something is going to be cooling down, then actually that's a way of actually removing heat. This is OpenStack's version of a bunch of different salts. Now, all a salt is a compound, an ionic compound, so these are different salts. And the ones with the positive slope up, what we have here is how many grams of solute per 100 grams of water would dissolve along the y-axis. So it's increasing going up, and over here along the x-axis we have increasing temperature. So if you increase temperature, you increase solubility, you get the positive slope sort of thing. There's only one on here that I see with actually a negative slope. This would be the cesium-3 sulfate, this guy right here. So check this out, and it's not the only one. Actually, ammonium, right? Ammonium chloride is another example. Things that get, that's right, things that get cold or hot, I don't know. But anyway, this isn't the only one that has this negative slope, but as we increase temperature, solubility decreases. I wish we had a few more of those. This is ammonium chloride, and ammonium chloride is the normal one, where as you increase the temperature, more will dissolve. In this case, I'm going to show you as we decrease the temperature, less will dissolve. So if we take ammonium chloride, it's all dissolved and everything, but if we cool it down, it's going to precipitate out. Okay. This is going to talk us through what happens when something dissolves, and you're going to see actually we can kind of piece together the energies. So here we're breaking the potassium cation and the fluoride anion bonds. Okay, that would be the delta H of the lattice enthalpy. And here we're actually adding water molecules, the enthalpy associated with the hydration around the cation and the anion. So again, notice this is endothermic, this is exothermic. So what we've learned about enthalpies is that you can it doesn't have to happen in this order, but if the overall enthalpies, or if the steps add up to the overall thing of interest, then you can add their enthalpies together to get the enthalpy of interest. Enthalpy for the overall thing of interest. That's exactly what we're doing here. So if you do the math, you actually end up with an exothermic process to dissolve the potassium fluoride. Again, now looking at sodium chloride, there is a positive enthalpy associated with endothermic to break those the crystalline lattice structure, This would be the hydration of the sodium cation, the hydration of the chloride anion. When bonds are formed, energy is released, thus they're exothermic. Okay, the overall enthalpy of associated with that process you can get by adding up those three enthalpies. Makes sense. Here are some enthalpies of hydration for various cations and anions. Okay. So this is a first, okay, come on. This is a first look at something called Le Chatelet's principle. So we're going to come back to Le Chatelet's principle. It's cool, no pun intended. The Chatelet's principle apply to equilibria, like this. I'm kind of get rid of my extra arrows. This is an equilibrium. Why is it an equilibrium? Because it goes forward and it goes back. It's an equilibrium. Okay? It's not just a one-way sort of thing. So, the way things that we can do with regard to the Chatelet's principle and stressing an equilibrium. I kind of tease like it's minding its own business. It's the same rate in the forward direction, the same rate in the reverse direction. Things we can do to kind of stir things up. One is we can add a little bit of reactant or add a little bit of product. One is we can monkey with the temperature. We can change the pressure. These all have results on what your equilibrium is going to do. So let's go back to this equilibrium of dissolving a solid solute in a solvent. And let's just say that it's an endothermic process, as it's written. We're dissolving from left to right. We're dissolving our solid solute, liquid solvent, and getting a solution. So if it's endothermic, I guess I should put my heat back up there. If it's endothermic, we can think of heat as a reactant. They aren't all endothermic, but we can think of heat as a reactant. That's the case. Now, the way Le Chatelet's principle works, the way I think of it, and I have this one with you, is a bunch of pushing and pulling. If we add something, we push. If we take something away, we pull. And it's like tug of war. So in this case, if I add heat, can you see, since heat is on the left side, the reactant side, when I add heat, I am pushing. So the result is going to be more is going to dissolve. If this is an endothermic process, it's a push. System's no longer at equilibrium if I heat it up. That needs to readjust. This says that it's going to use up the extra heat that I gave it, and using the extra heat I gave it, it's going to proceed, what we say, to form products, which the products is the dissolved solution. So more will go into solution. The reactant will proceed from left to right, from reactants to products, and you're going to get more dissolved. So that's what we say if it is an endothermic overall dissolving process. Okay. So in other words then, most of those salts we saw, except for the cesium-3 sulfate, I think that's what it was, those were all endothermic dissolving processes. Well, what if it's exothermic? Well, if it's exothermic, I mean to kind of throw you off, but if it's exothermic, then I'm going to put heat over here. It's exothermic. Well, Chatelet's principle is about pushing and pulling. So if I put heat on the product side, and if I heat it up, I'm going to push it now. Okay. If I heat it up, can you see where if I push it, I'm going to get my solid solute back. Okay, so actually heating it up is going to do the reverse of what I usually think it does. Okay, so heating it up is actually going to form the precipitate. And this is the Adding is pushing, removing is pulling. So the system is going to have to use up the extra heat I added. And to do that, it's going to say, it's counterintuitive a little bit because we're all about left to right. But in this case, it's going to go from right back to left again. It's going to go from products back to reactants. What were my reactants? Well, they were my separate solid and liquid. Okay? So in this case, you're going to actually see some solid precipitate form when you heat it up. So to me, the salts we looked at, the only one that would fit this bill would be the cesium-3 sulfate, whatever. But some things are actually exothermic. You dissolve them. Okay, so that was a first look at Le Chatelet's principle. Again, we're going to be coming back to that in different units. So the solubility of a solute will decrease with increasing temperature. That's exactly what we saw with that one salt. It must be, is it calcium chloride? I can't remember. I don't know. So if you're dissolving it, it should get hot. And I'm pretty sure calcium chloride gets hot and ammonium chloride gets cold. So lowering the temperature would be like, you'd have to use pulling with regard to Le Chatelet's principle. So in this case, if we lower the temperature, instead of pushing from this side, we would actually pull from this side. And so lowering the temperature is going to make more dissolving occur. Okay, in this case. And then it's the opposite in the endothermic that we did a minute ago. All right. So, another thing, switching gears a little bit, instead of a solid solute, we're going to go to a gas solute. Anybody drank any pop lately? Yeah, right. So that's where you have gas dissolved in sugar water, basically. Gas is carbon dioxide. In most cases, if your solute is gas, then it is, what do I have here? It's an exothermic process. Okay. So gas is a solute, exothermic. So it makes it look like this, where we have something like CO2 or O2 or N2 trying to dissolve it in a liquid solvent, and it's going to release energy. So in this case, again, according to Le Chatelet's principle, if I add heat, if I add, I'm pushing, and where am I pushing? I'm pushing from the product side toward the reactant side. So that means you're going to have less dissolved and more of the individual. So here's the deal, like if you were to get a cup of cold water and set it out, okay, you might come back later and you'd see like little bubbles. Okay? And what's happening is de-aerating, instead of aerating. And your gas is coming out of solution. Lowering the temperature, the solubility of the gas. So it must be, I must have said that wrong. If you take hot water and cool it down, hot, it's less soluble. Cool, it's more soluble. I have to think. I might have just said it backwards. I think I did. Did I say it right? Okay.
If it warms up to room temperature, then the gas doesn't dissolve. That's why they're bubbles.
Because it was cold. Okay. So cold and then warm. Addition of heat. Yeah, okay, good. I did say it right. Okay, thanks. Yes. Okay. Very good. So most, this is an exothermic process for most gases dissolved in a liquid solvent. So then that means that they're kind of like the cesium sulfate, that if you increase temperature, then their solubility decreases. Cool. So here are some gases dissolved in water. In this case, the solubility is not given in grams of solute per 100 grams of water. It looks like it's given in moles of solute per liter of water at a particular temperature. Oh, sorry, temperature is varying. So in all these cases, the negative slope, is saying that as you increase the temperature, the solubility goes down. Which is the direct opposite when we think of trying to dissolve more and more sugar in water. Carbonated beverages. Or that's in carbonated beverages. This is chilled water. Small bubbles of air in this glass of chilled water form as it warms. Cool. Now we have a sad picture coming up. Sad picture alert. There you go. Sad picture alert. So the problem is when we have warm water, then it can hold less oxygen. Of course, our fish are counting on getting their oxygen from the water. Okay. So this is just picking on oxygen. How will it dissolve in water at these certain temperatures? So is the solubility going to increase or decrease as you go from the top to the bottom? As you go from cooler to warmer temperatures, it decreases. So it starts up here, and again, this is different units than we did with the grams of solid solute per 100 milliliters of water. But in parts per million, it gets lower and lower and lower at the higher temperatures. Ta-da! Okay, you knew it was coming. So this will be due all my classes. Man, I'm getting done early. So that's it. And the lab you guys are doing Thursday, we need to get to a certain spot on Wednesday because we haven't talked about the chemistry yet. But we'll get there. No worries.